Hi, welcome back to the lecture series on abstract measure theory with course code MTH701 and MMTE 305. As in our previous lecture, its video was missing after 20 minutes. Therefore, we continue our previous lecture from 20 minutes ahead, where from the video was missing. In that video, we have shown that the every open interval can be expressed as the finite disjoint union of increasing sequence of bounded open intervals such that each bounded open interval is contained in the closure of A, B. So in that video, we have shown that every thus every interval A, B, whether it's bounded or unbounded, can be expressed as the countable union of it's not disjoint as a countable union of bounded open intervals, union of bounded open intervals such that you can see from the cases 1, 2, 3 such that every bounded interval is contained in AB, is contained in the interval A, B. This we have seen. Now since our function is monotonic increasing, therefore its left hand limit and the right hand limit will exist at each point. So let's take any point in the interval. Therefore every interval can be written as this. The countable union of the can be expressed as the countable union. Okay, countable union of bounded open intervals. So therefore it is thus. Therefore we can assume that A, B is a bounded open interval. Now let x naught be any point in A, B. Now since f is increasing, therefore left hand limit and right hand limit of f exist at x naught. In fact these limits are actually this left hand limit is at the point x naught, which is the limit x approaches to x naught minus f of x, and that you can see it's equal to the supremum of f of x, such that since x is approaching to x naught from the left, so that means x is less than x naught, and obviously x is greater than A also. A less than x naught. So why it's a supremum? This limit is always a supremum because the function is monotonic increasing. So that means this f of x is always less or equal to f of x naught. So which means the limit for any such point x which is less than x naught. So that means the limit whenever x is approaching to x naught, this limit must be equal to the supremum of f of x, and this exists. This exists because f of x naught is some fixed. Its upper bound is actually f of x naught, which is a finite number. So that means this set is actually bounded, and it's also it's also like it's also increasing set. You can see, because you are taking the points which are approaching to x naught. So that means that means this supremum always exists actually, or you can say supremum of the set always exists. This whenever x is less than x naught, the supremum of the f of x such that x less than x naught, this supremum exists, and this supremum is actually the limit, left hand limit. That's why I have already said that the left hand limit exists. Also the right hand limit as well exists. So also the right hand limit, this limit also exists, because this is the limit from the right f of x. So it's plus sign here. So that means this x is greater than x naught. It's equal to the infimum of f of x. The reason is the same, function is monotonic increasing. So this x is greater than x naught. This x is greater than x naught less than x, but it's always less than b. So one more thing is that this every element, every number, or you can say every point of this set is greater than the every point of this set, because any point of this set it is actually f of x where x is greater than x naught, and here it is f of x where x is less than x naught. So in that the x of this set is greater than x naught, and x of this set is less than x naught. So that means f of x of this set is always less or equal to f of x of this set for any x. Or you can say, if you write here y, so that means this f of x is always less or equal to f of y for any x in this set, in x less than x naught, and for any y greater than x naught. So in other words, we can say every member of this set is actually upper bound of this set. So that means the supremum is less or equal to the each member of the set. So whenever supremum is less or equal to each member of the set, that means supremum of this set is the lower bound of this set. So which means that supremum is less or equal to the greatest lower bound of this set. The next this set f, this one which is where you are taking the infimum. Okay. So here this is f of x naught, which is equal to the supremum of f of x, a less than x naught, and this is f of x naught plus, which is equal to the infimum of f of x where x naught less than x less than b. So I'm telling that this value of this function is always greater than the value of this this value, this number. If I change the point x, if I write here y greater than x naught, then this is f of y here. This f of y is always greater or equal to this f of x for any x less than x naught, because for any such x less than x naught, it's always less than this y. If I write here y, so any x of this set is less than any y of this set. So that means f of x is less or equal to f of y. Here it is f of x, here it is f of y. F of x is less or equal to f of y for any x and for any y. Now if you fix y, and if you vary x, so that means any member, any element of this set is less or equal to f of y, where that f of y is the member of this set. So in other words, that f of y is actually upper bound of this set. So that means the supremum of the set is less or equal to f of y. Now you vary y. So that f of y is greater or equal to that supremum, is greater or equal to the supremum. This means the supremum is actually lower bound of those f of y's. If you vary the y where y is greater than y naught, x naught. So in other words, the greatest lower bound of that set will be greater or equal to that number, that supremum. So therefore we can say, so then if this f of x naught, it is always f of x naught plus is always f of x naught minus is always less or equal to, moreover this f of x naught minus is always less or equal to f of x naught plus. So this I have explained why this is true. F of x naught minus is always less than or equal to f of x naught plus, because function is monotonic in decreasing. That's the main reason. So if the equality holds, then they must be equal to f of x naught. If f of x naught, if f of x naught minus is equal to f of x naught plus, because this f of x naught plus is less or equal to f of x, and f of x naught minus is greater or equal to f of x. So you have here f of x less or equal to f of x naught, sorry. So this is f of x naught plus, and it's the infimum of this set. So it's always greater or equal to, sorry, it's greater or equal to f of x naught, and this is less or equal to f of x naught. So if these two are equal, if left hand limit is equal to right hand limit, then using the monotone property again, then f of x naught is equal to f of x naught plus, which is equal to f of x naught minus. So you will verify this yourself. So therefore f is continuous. Therefore f is continuous at x naught. So whenever equality holds, whenever left hand limit is equal to the right hand limit, then the function is continuous at that point. But actually we need to find the points of discontinuity of the function f. We want to calculate the number. What is the set of the points of discontinuity of the function f? We need to show that set should be countable actually. So now we see if the point x naught is the point of discontinuity, then what will happen? We'll see that, and we'll try to find, we'll try to calculate those points actually. Now if f is not continuous at x naught, then obviously this f of x naught minus is strictly less than f of x naught plus. So therefore we can define the interval, that's called the jump interval. Therefore in this case, therefore we can define the interval that we denote by j of x naught, which is called the jump interval. Sorry, it's jump interval. It's called a jump interval. Called the jump interval at x naught, and is defined by, that's the notation denoted by j of x naught, called the jump interval. Now we define it, and is defined by, what is the jump interval, and is defined by j of x naught, those points such that they lie between f of x naught minus and f of x naught plus. Okay, because this is now strictly less here, so there are points between these two points, f of x naught minus and f of x naught plus. So let's denote that set by g of x. It's obviously an interval now, and you can see this interval. It is a subset of, obviously it's a subset of f of a and f of b, where this f of a and f of b is a bounded closed interval, where this f of a, f of b, where f of a, f of b is a closed bounded, as a and b are finite numbers, it's closed and is a closed bounded interval. So we have the situation like this. This is the closed and bounded interval, okay, f of a, f of b, and this is the point of discontinuity x naught, and here we have a jump interval. Say this is here f of x naught minus sorry, it is here f of x naught, not this f of x naught, and here is a jump around this point f of x naught plus. So for any such point we have a jump interval where the function is discontinuous around the point f of x naught. If the function is discontinuous at x naught, then we have a jump interval around this point f of x naught. Okay, this is the jump interval. Now how many jump intervals are possible? Suppose if we choose any natural number n, I want to calculate the jump intervals of length 1 by n. Obviously they are finite. Suppose for n equal to 1, so how many jump intervals are possible of length 1? Let me assume that suppose the length of this total interval, because each jump interval is subset of this interval, and one more thing is that these jump intervals are disjoint. Also I want to first mention that also the jump intervals are pairwise disjoint. Pairwise disjoint means that is if x1 and x2 are points of discontinuity then we have jump interval at these points. Those jump intervals are disjoint. They are denoted by j of x1 intersection j of x2. So this intersection is the empty set. So one thing, this is finite. Okay, f of a, f of b is a finite. It's a closed, not finite. It's a bounded interval. And the function and the point where the function is discontinuous, we have a jump interval which is subset of this interval, and these jump intervals are pairwise disjoint. So if the length of this, it's a finite length, suppose its length is 5 say, then how many jump intervals are possible of length greater or equal to 1 or less or equal to 1, you can say, of length say greater than 1? How many jump intervals are possible if the total length is 5? And how many jump intervals are possible of length greater than 1? That cannot be more than 5. That cannot be more than 5, because total length is a 5. Similarly, if the total length is suppose 100, how many jump intervals are possible of length greater than 1? It cannot be more than 100. Similarly, if you choose n equal to 2, then we have 1 by 2 here. How many jump intervals are possible of length greater than 1 by 2? It again depends on the length of the interval. If it is 50, then the total number cannot be greater than 100, because you are taking now half, 1/2. Similarly, 1/3, you will have say 300. You will have 300 if the length of the total length of the interval is 100. You have 300 jump intervals, at most 300, not more than 300. So what I mean to say that for any natural number n, there are only finitely many jump intervals of length greater than 1 by n. Okay. So if you vary these n, you will get the total number of points of discontinuity. That's the union actually. Let's suppose that for n equal to 1, let E1, okay, E1 be the set of the discontinuity. Obviously, in that case, if n is equal to 1, we have suppose the length of suppose the total length is 5, then we have five jump intervals. At most of 5, say j of x naught, j of x1, j of x2, j of x3, and j of x4, say. So these points x naught, x, they are the points of discontinuity. In that case, our sets like this: x naught, x1, x2, x3, x4. Not more than this. It may be less than this. Okay, at most this. And now suppose n is equal to 2. So I am assuming that the length is total length is 5. Okay. If n is 2, then how many jump intervals are possible of length greater than 1 by 2? That's 10. Then in that case, we define E2. We had 10 jump intervals. That means we had 10 points of discontinuity. Say y0, y1, y2, so on. So if we do this for each n, we will get the total. We will get the whole set of discontinuity of the function of that's equal to the union of these sets actually. And each set is finite. It's a countable collection of finite sets, and the union must be countable, because we know that countable union of countable, because each set is countable. Each set is finite. Every finite set is countable. So the set E where the function is discontinuous, it is the union of those sets. is obviously a countable set. So these jump intervals are disjoint. This is an exercise for you, and from this you will conclude that for any natural number n, the number of the jump intervals of length greater than 1 cannot exceed, is always finite, and what is the number depends upon the total length of the interval f(b). So therefore, since the jump intervals are disjoint, therefore for any natural number n, the number of jump intervals of length greater than 1 over n is always finite, is always finite. This I have explained why it's finite, is always finite, and hence the set of the points of discontinuity, hence the set of the points of so let me elaborate it more. Okay, I will write here. Okay. let j of say x11 comma j of x11 comma x12 so on up to j of x1m be the jump intervals of length greater than 1, comma j of, now I define j of x21, j of x22, j of x2m be the jump intervals of length greater than 1/2. Okay, in general let j of x and 1 comma j of x and 2 so on j of x and m. So these numbers may be different, so I will write instead of m always, I will write first here m1, the first stage m1 up to m1, and second stage up to m2, and at the nth stage I'll choose m subscript n. Okay, let these be the jump intervals of length greater than 1 by n. Then the set of points of discontinuity is, that's this set. First we have this x11, x12 so on up to x1 m1 union x21, x22 so on x2 m2 union continue. This is true for each n, so n runs from 1 to infinity. So it's actually a countable set which which is a countable set, which is a countable set. Hence the set of points of discontinuity is countable, is countable. This proves the theorem completely. Now next theorem, which is also very important because as in the chorus topological space you have seen that there does not exist a function f from R to R. There does not exist a function from R to R such that this function f is continuous at each rational and discontinuous at each irrational. This you have seen in the chorus topological space. There is no such function which is continuous at each rational and discontinuous at each irrational. In the next theorem, as an application part of the next theorem, we will see that there exists a function f from R to R such that this f is strictly increasing, more stronger than continuous, strictly increasing, continuous at each irrational, not rational. It is the reverse of this actually. Continuous at each rational and discontinuous at each rational. Okay, we'll see this function always exists. It's an application of the next theorem actually. Discontinuous at each rational, continuous at each irrational and discontinuous at each rational. That's the application of the next theorem. So let me first state this next theorem. So the important thing is that the set of rational numbers is countable. That's what we are doing in the next theorem. Given a countable set, we will see that there is always a function which is increasing. Okay, so let's state this theorem here. If let C be a countable set, let C be a countable set. Countable subset of AB. AB is an interval. It may be bounded or unbounded. Then this theorem states that then there is an increasing function. Then there is an increasing function f from AB to R that's continuous only at these points outside of C, only at this set AB minus C. That means that function is not continuous at any point of C, but it's continuous at every point of AB minus C. So as an application part, you can take this C as a set of rational numbers. That's a countable set. So there is a function from this to this which is continuous only at AB minus Q. That means it's continuous only at irrationals and discontinuous at each rational point. and here this function is an increasing function, but in case if c is q, that this function is strictly increasing. Why it is strictly increasing in that case, that I will explain by after proving this theorem. Now first case, this since C is a countable set, it may be finite or countably infinite. The first case, if C is countable, if C is finite, sorry, if C is finite, if C is finite, say this C is equal to, say it's equal to say A1, A2, AN subset of AB, then the result is trivial. Then define let's see be this such that A less than A1 less than A2. I can write these numbers in order because it's a finite set, it's a discrete set here. Okay, then we define the function like this. We have the set here A, B, open interval. It may be whole real line. Then we have points A1, A2, and so on up to here A n minus 1. Then we have point A n. So let's define the function by f of x is equal to say 0 if A less than x, say less or equal to A1, and then I define it 1 if A1 less than x less or equal to A2, and then I define it 2 if A2 less than x less or equal to A3, and continue. We'll do this continue. We define that the last an on the last interval it's n if an less than x then less than b. You can see this function, it's continuous on each open interval. So on open interval a1, on open interval a1 to a2, then open interval a2 to a3, and so on, then the open interval an minus 1 to an, and then the open interval an to b. But it's not continuous at these points a1, a2, so on up to an. That means it's not continuous at any point of c, but it's continuous outside of c. Why it's continuous outside of c? Because on this open interval its value is 0, that means it is constant, and on this open interval its value is 1, that's constant, and constant is continuous, so it's continuous on this open interval, and it's similarly it's continuous on each open interval because it's constant on each open interval. And it's not continuous at a1 because the value of the function at a1 is 0, but when we take the limit of the function from the right hand side it's 1. So it's not continuous at a1. Similarly, it's not continuous at a2, and in general it's not continuous at an minus 1 an. And one more thing is that it's increasing function. So then this function is increasing, then f is increasing, then f is increasing, and continuous only at the set A, B minus these points minus C. So in that case the result is done. Now next we assume that case second, if this C is countably infinite, then in that case we cannot write the set as in the order like this, increasing or decreasing order. This is not possible for a countably infinite set. Okay, why it's not countable? Because if you take the set of rational numbers, suppose you start with 1, then you cannot find the next rational number which is greater than 1. That's not possible. So that thing is not possible for countably infinite set, which is possible for finite set. Here you have written those numbers in increasing order. So what we do in this case, we define a function here. and let's see the countable infinite set, and let's enumerate but we can enumerate these points. Let q1, q2, so on up to infinite. This is an infinite set, countable set. Be the enumeration of C, because C is countable. Now we define function. Define a function. Define a function f from AB to R by. Define this function by f of x equal to series 1 by 2 power n, which is always convergent series, and it is sub series also convergent. So here it's not the exact whole series, it's a sub series, like it's sum runs over those n's such that qn is less or equal to x, and this function is properly defined, which is properly defined, which is properly defined as the whole series. If you take whole series 1 by 2 power n runs from 1 to infinity, is convergent, is so its sub series is also convergent. So how we have defined this function, let me explain it here. We have an interval AB, then we have the points q1, q2, like q2 may be here, then q3 may be here, then q5 may be here, then q6 may be here. It's not in the increasing order, okay? Then say q10 may be here, then q9 may be here. So this is countable infinite subset of the interval AB. Then let's choose this point here. I want to define the function f of x at this point. What's this f of x? If the points are like this, those points q1, q2, they are that in countable infinite sets like this on the interval AB. Then if you choose this point x here, though you want to calculate f of x. What's f of x? It is n. It's 1 by 2 power n. Where what is this n? N is such that q1 less or equal to x. So what are those q1s here? Only q1 and q5. These two are less or equal to x. So that means n has only two values, 1 and 5. So therefore this series is equal to 1 by 2 power 1 plus 1 by 2 power 5 for that x. Now if you choose x here, obviously again we have some points. We have here we have q2, q3, q1 and q5. So the values of n are 1, 2, 3, 5. So that means this series must be equal to this series. In that case, f of x is equal to 1 by 2 power 1, 1 by 2 power 2, 1 by 2 power 3 and 1 by 2 power 5. And now if you want to define it for this x, so its value is 0 because we don't have any q on this side. Now suppose if you want to define x, if you want to define the value of the function for this x, and in that case all the q's on this side, so that means in that case it is whole series 1 by 2 power n and its value equal to 1 at that point. So this function f is properly defined because the series is convergent. Actually its common ratio is 1 by 2, and I have explained it how it's defined actually. Okay, next we will see that this function is monotonic increasing. It's continuous on it is discontinuous on each point of C. That means it is discontinuous at q1, it is discontinuous at q2, q3, so on each point, each q's, but it's continuous on the rest of the set. That means it is continuous on AB minus C. We'll check those properties. The first property we'll see, the f is increasing. F is increasing. So let's check this f is increasing. So how do we do that? We choose any 2 points here in the interval AB, u and v, such that this u is less than v. We show that f of u is less or equal to f of v. So obviously there are q's now because this is the interval AB, and C is a subset of A, B. It's a commutable set. So there are, say, let's suppose that there is Q3, Q4, and let's suppose that there is, say, Q9, and let's suppose this is here Q2. Suppose it's Q2 here, and it's suppose here, say, it's here Q9. Suppose. Then if you want to see what's is f of v is bigger than f of u, which one is greater here? And here you see f of u is equal to 1 by 2 power 3 plus 1 by 2 power 4, but f of v is equal to 1 by 2 power 3 plus 1 by 2 power 4 and 1 by 2 power 9. Obviously it is greater. So then let me put increasing like this. Let u and v belongs to the interval a, b, such that u is less than v. Then what's this f of v minus f of u? I want to show that this is greater or equal to 0. This is the summation n. It's 1 by 2 power n. Summation n such that it's f of u minus f of v. F of v minus f of u. So that means you have to subtract this portion actually. You have to remove those n's actually, which are corresponding to those q's which are less than u. Okay, so it's like this. Q it's like you can see it is like this. It's q. It's u less than qn less or equal to v. Only those q's which lie between u and v, but they are strictly greater than u. So if you see this sum for this particular case, if you want to calculate f of v minus f of v, what's f of v? F of v is 1 by 2 power 3 plus 1 by 2 power 4 plus 1 by 2 power 9 minus f of u, it's 1 by 2 power 3 plus 1 by 2 power 4. So 1 by 2 power 3 and 1 by 2 power 4, they will go with the minus sign. There remain only 1, that's 1 by 2 power 9. That means those n's which correspond to those q's that lies between u and v. That's why I have written here those qn is such that u greater than qn and qn is less or equal to v. And this is always greater or equal to 0. In general it's not greater than 0 because there may be no any q in this interval. Then in that case f of v and f of u, they are both same because all the q's are here. F of v is the sums over those q's, f of u is sums over those q's. It's f of v minus f of u, that's obviously equal to 0. But in the case that there is some q, suppose there exists some q lying between u and v, then in that case it's strictly greater than 0. But in general it's greater or equal to 0, which implies that f of u is less or equal to f of v. So that means f is increasing. F is increasing. Next we show that f is discontinuous on C. F is continuous at each point of C. F is discontinuous at each point of C. F is discontinuous at each point of C. Okay, that is second property. F is discontinuous at each point of C. Each point of C. Let x is equal to q, k, it belongs to C. We show that this is it's the point, it's some fixed point x naught. Okay, and let's choose any point. Let x is any point which is less than x naught, then we have seen that. Then what's this f of x naught minus f of x? This we have seen, it is a summation. It's a summation 1 by 2 power n, those n is such that it's minus f of x such that this x is less than qn and less or equal to x naught. Okay, and we know that at least one qn lies in this interval, that's qk itself, because qk is less or equal to x naught and it's greater than x. Okay, x naught is qk. So that means this sum contains at least one term, which is 1 by 2 power k, because qk is here, but it may contain more than those terms. So in general it's greater or equal to 1 by 2 power k, as x less than qk less or equal to x naught, because this x naught is here qk. Okay, so that means for any point x which is less than x naught, this difference is always greater or equal to 1 by 2 power k. It's independent of this x. So if x is approaching to x naught, this will always remain greater or equal to 2 power k. So that means if you decrease the distance between these 2 points x and x naught, the distance between the points f of x, between these images f of x naught and f of x, will never get decreased. It will always greater or equal to 2 power k. So that means this function is not continuous at x naught. So this implies f is not continuous at x naught. Now third property, f is continuous on this ab minus c. Okay, it's continuous on this set ab minus c. Okay, so let's choose any point in this set. Let x naught belongs to ab minus c. Okay, let's choose this point ab minus c, and let n be any natural number, any it's like this. Okay, it's ab, it's here, there, these are the points, these are q's, and there is some point x naught which is not any q. So this is suppose here, suppose this is q3, this is suppose q1, this is suppose q7, this is suppose q2, this is suppose say q10, this is suppose q9, and suppose this is the point x naught, it's x naught. Okay, this is the point x naught here, which is not in C, which is not any of Q. It's different from Q. Okay, so for this point Q, and for any natural number n, I can find interval. I can find interval which obviously very small. I can find, say, this interval around x naught, such that this interval does not contain any points, say q1, q2, these finite points qn. Okay, so these qi's, q1, q, they may be close to x naught, but I choose interval I so small such that, because there are finitely many points actually, that's why I can choose this interval. This interval, it may contain some q, it may contain some q, but when I fix any finite number of q's, q1, q2, q1, I can always choose an interval I such that this interval does not contain any such point, any such q, q1, q2, qn. And rest of the points, it may contain rest of the whole rest of the set, or it may contain say q1 plus 1, q1 plus 3. Not all the q's other than these q1, q2, qn is so it may contain the other points of q, other points of c other than these q1, q2, qn, or it may contain all the points of c other than these q1, q2, qn. This may happen, but I can always choose this interval I at the point c. I can at the point I can find this interval which contains the point x naught, such that this interval does not contain any point q1, q2, qn. Okay, this interval can be chosen. So because you can find the distance of q1, because q1 is not equal to x naught, q2 is not equal to x naught, and so on, q1 is not equal to x naught, and x naught is not in C. So you can choose a distance. You can find the distance between x0 and q1, x0 and q2, so on x0 and qn. You can find all such distances. If you find all such distances, then you choose the minimum distance and you find the interval of length that minimum distance less than the minimum distance, and you will see that interval does not contain these points, because if it will contain the any such point, then the distance must be the distance must be less than the minimum distance, which is not possible. Okay, so this interval can be chosen. This interval can always be chosen. We can choose this interval. So let n be any natural number. There is an interval. There is an interval. There is an interval. There is an interval I containing x0. There is an interval I containing x0 for which qk does not belongs to I for 1 less or equal to k less or equal to n. So this I have explained how it is possible. Now let's say x less than x0. Let's choose any point x less than x0. Then I want to find this f of x0 minus f of x. It's again the sum 1 by 2 power n, those n's such that this x less than qn less or equal to x0. So you want to find you have an interval I here. This is an interval I. It contains a point x0 and it does not contain those points, but it may contain the points other than the q1, q2, q1. So it may contain q1 plus 1 or it may contain q1 plus 2. Suppose it may contain all those points q1 plus 1, q1 plus 2, then the series is equal to 1 by 2 power n plus 1 plus 1 by 2 power n plus 2 plus so on up to infinity. Or if it does not contain each such point, each such qn plus 1, qn plus 2, then this sum is less than that series. So in general I can say this series this is less or equal to, I can say this is less or equal to 1 by 2 power n plus 1 if it contain all the points qn plus 1, qn plus 2, this interval. Okay, because x is here, x is less than x0, x is less than x0. So f of x0, I want to find qn is lying between x and x0. So suppose if it contain each qn plus 1, qn, if it's not containing those points q1, q2 up to qn, because they are outside of this interval, but the rest of the points qn plus 1, qn plus 2, they may in this interval I, or not all, but some of them, or it may be possible all of them are in this interval. So in general it's lesser. Suppose all of them are there, then equality holds. If all of them are not there, then it's in general it's less or equal to 1 by 2 power n plus 2. This is the series, and you can see this is equal to 1 by 2 power. It's a geometric series. You can calculate its sum. Its first term is 1 by 2 power n plus 1, and its common ratio is 1 by 2. So its sum is actually 1 by 2 divided by 1 minus r. 1 by 2 power n plus 1 divided by 1 minus r is 1 by 2. It's 1 by 2 power n plus 1. So its sum is like this. First term, that's 1 by 2 power n plus 1 divided by 1 minus r. 1 minus r is 1 minus 1 by 2, that's equal to 1 by 2, which is equal to 1 by 2 power n. So it cannot be equal to this 1 by 2 power n for each n, because this x is fixed actually. So here I can write it strictly less, not less or equal to. Okay, it's strictly less. So if this x is approaching to x0, this distance is less than 1 by 2 power n. That means f of x is approaching to f of x0, which means the function is continuous at x0. And if you choose x greater than x naught, then you will change it here. Then you will write here f of x naught, f of x minus f of x naught, and you will again see it's less than 1 by 2 power n. So in general, if I let x be less than x naught or x naught be less than x, then you can take the mod in general. Okay, this mod is less than this. So therefore this f is continuous. F is continuous at x naught. So that and this completes the proof of this theorem. So already I have mentioned that for if C is a set of rational number, then this function is strictly increasing. Why it is strictly increasing? Because the reason is here. This is the reason where we have seen that this function is monotonic increasing. Look at this. I have written here greater or equal to 0. Why it may be equal to 0 if there is no any point between u and v. If there is no any q between u and v, then this is equal to 0. If there are q's between u and v, then this is greater than 0. Okay, here if there is any q between u and v, then this sum is greater than 0. If there is no any q between u and v, then this sum is equal to 0. But if our C is q, set of rational numbers, then there is always a rational number between u and v. So in that case this is greater than 0. So that means f of u is strictly less than f of v, which means f is strictly increasing if C is a set of rational numbers. Okay, now in the next theorem we will define Vitalik cover, then we will prove Vitalik covering lemma, and finally we will use the Vitalik covering lemma to prove the Libig's theorem, which states that every monotone function is differentiable almost everywhere. That's a very important theorem. That's from Libig's theorem. Every monotone function is differentiable almost everywhere. Okay, so